For most facilities, electric power to operate motors is a substantial cost. Motors and the equipment they are connected to represent substantial capital cost, operating cost, and loss of production when equipment is out of service. I did an informal survey at our own house to see how many motors we have, and around 35, to my complete total surprise, I stopped counting. There were more. So the $64 question is, how many motors have you got in your facility? And more importantly, how many horsepower do you have installed? Electric motors globally consume about 45% of the total amount of power on the grid, which is a remarkable number when you think about it. Electricity really did two things for civilization. It took us out of the dark of the night, and it gave us the ability to take electric power and create rotary motion. And once we have rotary motion, we can do linear motion, and we can perform work. The important thing to remember is the relationship between work and horsepower. Horsepower being measured in kilowatts is 0.745. If we want to get fancy about it, which I like to use simple numbers, just figure it's about 75% of the horsepower rated for the motor. So a 10 horsepower motor will draw about 750 watts or 0.75 kilowatts of power. As an example, a 10 horsepower motor operating at 10 kilowatts per hour is going to consume about $3,700 worth of electricity a year. The essential thing to recognize is that 10 horsepower motor is about $1,000. So you've got a piece of equipment that's consuming at least 3 to 4 times the amount of power in 1 year that you're putting out in the cost of putting the motor in. The question is then, how do you monitor what's going on with the motor? Well, a current conventional way to do it is to put a circuit breaker or a circuit transformer and read the amount of amperage going into the motor. As this slide shows, power measured by amps is a short parabolic curve, and you don't have the ability to really do a lot of measuring. So the better way to do it, to measure power, is to measure the voltage and the amps, and that gives you, first of all, a linear curve, which gives you the ability to manage the information much better, and more importantly, it gives you the ability to profile what's going on. If we take a look at a pump, we can see that as we look at the power consumption of this pump, depending whether it's open, closed, full flow, valve control valve, all the kinds of things that a pump's going to face, the amp draw on a pump is a function of the amount of water it's moving. That's the work that's being performed. So if I want to move 10 gallons a minute with a pump that's rated at 100 gallons a minute, then that pump is not doing a lot of work. Therefore, it's not drawing a lot of power. On the other hand, if I'm going to be pumping 100 gallons a minute, then that motor is going to have to ramp up and run at full power. A motor is a dumb piece of equipment. And what do I mean by the word dumb? Well, very simply is, it just wants to consume as much power as it can until it goes to self-destruction. So if I've got a 10 horsepower motor and it's driving a load which is currently consuming 7 horsepower, then that motor is just sort of loafing along. As the work on the motor increases and it gets up to 10 amps, and then something starts to fail, a bearing goes out, something changes in the process, which means it's going haywire, without the insertion of a circuit breaker or a fuse, that motor is going to continue to draw motor until it just simply burns itself right out. What's the solution? Well, quite simply, it's to take a device called a load control sensor. And what that load control sensor does is measure the voltage and the amp draw. Therefore, we have the power consumption of the motor. And that becomes the way now to look at sort of a linear line, and we can profile what the motor is doing. So let's take that idea and move a step further. One of the most common uses of motors in an industrial plant is to move things around. So you have conveyors, indexing machines, machines that wrap, shrink, do all kinds of things. In almost all cases, they involve motors. Since we've got rotary motion and linear motion going on, then the big issue is as that machinery begins to wear out and friction becomes an issue, the power consumption goes up. So the key is to use a load control sensor again, profile what's going on, and once I've got a profile, when I deviate from that profile, I can now trigger an alarm or say something is happening, something is wrong. And that's the key with a load control device. Let's look at one other process application, and there's myriad process applications. Let's say that we're doing a mixing operation. So we dump a bunch of ingredients into a container. The viscosity is slight or low. As we turn the mixer on and we begin that mixing process, and the chemistry of the things we're mixing together changes, the viscosity goes up, and therefore the load on the mixer starts to increase. Something goes wrong either in the mixer or in the batch of the load, and it starts to really jump up there. We get out of profile, again we trigger a warning. Load control power centers come in a number of different versions. There are some that are specifically made to operate with pumps. There are other options available on the sensors. We can go up to about 150 total horsepower as the largest units that are available. Without going through all the details of the load controller, let's go back and just simply say we have the ability to profile. Once we can profile, we can program. You can take a look later at the information, but the key issue is pretty much whatever wish you have to profile an alarm, and basically you have 3 different points on the curve that you can profile. You can trigger an alarm, you can shut a piece of equipment down, you can get onto a wired network or a wireless network and transmit that information back to a control room. So the essential point is whatever you want to do can probably be done with a load control device. The other thing with a load control device is you have to ask the question is, well, how much is this wonderful thing going to cost me? The best way to assume what it's going to cost you is whatever you're currently spending for from a 5 to a 10 horsepower motor, that's about what a single load control is going to cost you. So even for a motor down at that size, which is going to consume that $3,500 to $4,000 of electricity, if I can save 10 or 15% of that electricity, I'm going to get payback on the motor. If I protect a piece of equipment from going down, I get payback on the load control. So really, anywhere you go is win-win.